This right here is the $14 billion Kansai International Airport in Osaka, Japan. It was built on 2 artificial islands with a total surface area of over 1,000 hectares. It sits in the Osaka Bay area, 5 kilometers offshore, at an average depth of 18 meters. The construction of the first island commenced in 1987 and finished in 1991, followed by the construction of the airport facilities, which took around 3 years. Kansai International Airport officially began operations in September 1994. In the 5 years of the island's construction, 3 hills were demolished to get 180 million cubic meters of granular fuel with a height of about 33 meters to place on the seabed. The airport was singled out by the American Society of Civil Engineers as one of the monuments of the millennium, a designation awarded to the 10 civil engineering projects deemed to have had the greatest positive impact on life in the 20th century. Which is kinda ironic because the airport is sinking, and it has been sinking since the beginning of construction in the 80s. However, this doesn't take away how monumental this modern engineering marvel is because, believe it or not, all heavy structures sink. In geotechnical engineering terms, this is called settlement. During the design phase of any project, the anticipated magnitude of the short and the long-term settlement can be calculated using analytical methods based on the geotechnical properties of soil in the subsurface and the expected load from the structure. With this information, solutions can be developed to either improve the ground material properties if excess settlement is anticipated, or adjustments can be made to the structure to compensate for the long-term settlements in the future. So, what went wrong in the design and construction of Kansai International Airport? My name is Chido Chashe. I talk about geotechnical engineering related topics, including construction methods, disasters, and past, present, and future innovations in ground engineering. Please, like and subscribe to the channel. With that, let's dive into the video and talk about the unexpected excessive settlements of Kansai International Airport. This is Geotechs with Clemens. Unlike road pavement construction, international airport pavement structures have stringent construction regulations around the world because of their inherent importance and focus on aviation safety. For obvious reasons, airports are built on huge plots of open flat land with good drainage. The airport runway has to be flat, which means that the subgrade materials should be compact enough before construction to avoid settlement. But what is this settlement? You see, the soil matrix is composed of discrete particles with voids in between, which are occupied by water and air. When a load is applied, the water is squeezed out, and the particles will shift and rotate to occupy the void spaces, therefore reducing the volume of the matrix, and this, as a result, will cause settlement. So, in theory and in practice, engineers can improve the subsurface by using chemical and mechanical techniques to compact the soil before laying the surface pavement and minimize long-term undesired settlements. However, engineers responsible for the design and construction of Kansai International Airport had limited choices of ground improvement techniques to implement. Remember, the average water depth at the proposed airport location was about 18 meters. This meant it was next to impossible to implement most of the conventional ground improvement techniques like the dynamic soil compaction, soil replacement, and chemical stabilizations. Furthermore, the airport at the time of construction was the world's first ocean airport built on artificial islands. Therefore, there was limited practical and technical guidance or literature that the engineers could refer to. The geological formation of Osaka Bay didn't make it easier either. The top 20 meters comprised of soft alluvial Holocene clay deposits, followed by alternation of sand and clay layers of Pleistocene origin. The Holocene clay in Osaka Bay is relatively soft clay with a hardness roughly equivalent to that of toy clay, and it can hold up to 70% of water by volume. This layer is made from relatively new materials deposited in the last 11,700 years of Earth's history. That is, the time since the end of the last major glacial epoch. Underlying the Holocene layer is the Pleistocene strata, which was formed during the geological period that began around 2.6 million years ago and ended around 11,000 years ago, the period commonly referred to as the Ice Age. The Pleistocene strata had a complex geological profile, with marine clay alternating with sand and non-marine clay layers, as well as a very thin volcanic ash deposits. The alternating sequence of marine and freshwater deposits is a result of lateral migration of the depositional environment caused by fluctuations in sea level. You see, during warm global climates, sea levels are relatively high. Therefore, the predominant deposits are marine clay layers, which are deposited by seawater, while non-marine clay and sand layers, which are deposited by rivers, correspond to cold global climates when large volumes of water are stored as glacial ice on the continents and sea levels are relatively low. Now that I have touched on the geological formation of Osaka Bay area, let me circle back and present a more technical description of settlement, which is more fitting to the conditions that the engineers were working with. In general, the settlements of saturated sand and clay materials are governed by different phenomena. Because of the high permeability of sand, meaning that the water in the pores can drain freely, the pore water pressure is considered to dissipate immediately when loaded, and the sand particles can quickly rearrange and densify. This means that settlements of saturated sand layers are normally immediate settlements unless under special conditions. On the flip side, clays have a low permeability when loaded. There is a rise in pore water pressure as it tries to drain, which takes time to dissipate. This makes the settlement of saturated clays time-dependent, that is governed by two processes. Primary consolidation, which is the decrease in the volume of pores due to the flow of water caused by dissipating pore water pressure gradient, and secondary compression, which is the decrease in pore volume due to creep. Faced with these complex geological conditions, the geotechnical engineers implemented an ingenious soil improvement technique to accelerate the compaction of the Holocene clay layer. Before installing the perimeter seawalls, a 1.5 meter thick sand blanket was placed on the seabed. 1 million sand drains were installed to fully penetrate the Holocene strata to connect the sand blanket and the underlying diluvial sand layer. The rationale behind this technique was to shorten the drainage path and utilize the permeability of sand to speed up the consolidation and compaction of the marine clay. And this actually worked. As reported by Handy in his 2002 publication First Order Rate Equations in Geotechnical Engineering, the top 20 meters of the Holocene clay reached almost 90% of its final settlement during the construction. These settlements were accounted for in the design and were compensated by adding an extra 6 meters of fill as well as increasing the height of the seawall. Due to the considerable depth of the Pleistocene strata, no viable measures were available to accelerate consolidation. Instead, a special effort was made to predict the settlement as accurately as possible. However, what was not accounted for were the excessive settlements of the Pleistocene clay and sand and their slow accumulation in time. In a 1999 publication, Settlement Behavior of an Offshore Airport, Akai and Tanaka presented field settlement data that had been collected since 1990 at the airport and compared it with the analytical settlement predictions used in the design. The field data showed that the island had experienced about 1 meter of immediate settlement in 1990, followed by an additional 5 meters of primary settlement between 1991 and 1995, and continued to increase at a rate of about 15 centimeters per year. These settlements were being contributed by the consolidation of the Pleistocene strata. The original design did not anticipate these developments, and this was a problem. You see, the extra layers of fill added during construction, which were derived from the analytical solution, only compensated for the settlements of the Holocene strata and a small portion of consolidation settlements of the Pleistocene deposits. So, as soon as it was clear that the Pleistocene sediments were the source of these excessive settlements, some attempts were made to re-evaluate and correct the original design based on the field measurements. But each time a prediction was made, the island provided a new surprise. First, it was the sizable immediate settlements. Next, it was a much slower than expected rate of settlement at the beginning of the consolidation. And finally, these settlements did not seem to slow down as much as it was expected towards the end of the consolidation. All these factors are rather difficult to accurately quantify in advance of construction, which is not good news for designers. Firstly, from the field measurements, one thing that was obvious was the immediate settlements in the Pleistocene strata. The sand layers in the strata compressed during and immediately after the construction of the island. This is attributed to the compressibility nature of sand, which has pores that are sufficiently large enough to allow the immediate dissipation of pore water pressure when loaded. The original prediction even captured this phenomenon. But how come there was a deviation between the predicted and the measured values? You see, the one-dimensional theory that was used to produce the predictions has a limitation. Clay, unlike sand, is less permeable. Therefore, the pore water cannot be squeezed out immediately when loaded. So, the theory makes the assumption that the immediate settlements in saturated clays should be zero. Basically, this meant that the immediate settlements in the clay layers were presumed to be negligible. In reality, however, there are always some immediate settlements caused by the three-dimensionality of the real problem, which involves significant lateral strains. You can think of this problem in this way. If we apply a vertical stress on a cube of saturated clay with impermeable but flexible boundary conditions, meaning that the pore water cannot leave the system, in order to satisfy the incompressibility condition, the lateral strains or deformations have to be accompanied by some vertical strains without any change in volume. Without going too deep into the mathematical formulation, it is possible to establish a timeline for the evolution of settlement once some soil consolidation parameters are obtained. Through conducting laboratory oedometer tests on small soil samples, the compression index of clay can be obtained, which is a fundamental index in predicting the rate of consolidation. In 1943, Dr. Terzaghi, in his book Theoretical Soil Mechanics, presented these two governing analytical functions. With the compression index in place, the amount of settlement at a specific time or vice versa can be established. However, the analytical functions can only produce accurate results if and only if the drainage path length is correctly estimated. This is because the rate of consolidation is determined to a larger extent by the length of the drainage path. Conventionally, a sand layer between two clay layers is considered to work as a drain, meaning it will transport the pore water pressure away from the sphere of stress influence. However, in the case of Osaka Bay Pleistocene strata, some of the sand layers proved to be lenses entirely enclosed within the clay layer that had insufficient thickness continuity and sufficient fine components in them, which results in the storage of undissipated pore water pressure in the permeable sand gravel layers for a long time. This was confirmed by the very slow dissipation of pore water pressure measured in the sand layers 10 years after the construction of the first island. The unforeseen sand lenses meant that the magnitude of the drainage path was underestimated, and as a consequence, the analytical method overestimated the rate of consolidation. You see, although the magnitude of the final settlement is independent of the rate at which it develops, it is still of equal importance. The Kansai International Airport terminal building was constructed with hydraulic jacks attached to the basement columns to lift it up and maintain its original elevation as the island fill was settling to prevent differential displacements to the structure. Without accurate rates of settlement, this meant that it was difficult to schedule maintenance in advance. Finally, right around 2001, it became quite clear that the consolidation process was not the only factor controlling the rate of settlement in the Pleistocene clay layer. From the initial analytical predictions, the consolidation or the first phase of the island settlement was expected to slow down around the 2000s when the excess pore water pressure was presumed to have completely dissipated and transitioned into secondary compression or creep settlement, which develops at a slower rate and has small magnitudes. In reality, however, this turned out not to be the case. The field measurements deviated even further away from the analytical solutions at a faster rate. In their 1999 publication at the 12th European Conference on Soil Mechanics and Geotechnical Engineering, Akai and Tanaka attributed this to the physical phenomenon of destructuring of aged clays. In 1999, almost 3,200 days after the end of the construction, the settlement of the Pleistocene strata had already exceeded 6 meters, which is more than the 5.6 meters that was predicted and kept increasing at an average rate of about 15 centimeters per year. As of the recording of this video, January 2024, the Kansai International Airport is still sinking, although the rate at which it is sinking has drastically reduced. From the settlement figures reported on the Kansai Airport's website, the Holocene strata reached its final settlement of about 6 meters less than a year after the end of construction, and settlement of the Pleistocene strata sits at about 9 meters and counting as per the last recording made in 2022, making the total settlement 15 meters, which is way more than the 11.6 meters that were initially predicted. Now the question is, what is being done to resolve this dilemma? There's nothing much that can be done to stop the settlement completely, except to implement mitigative measures to cope with the effects of excessive settlement. For one, the addition of the fill to compensate for these settlements after an artificial island is completed is often not technologically feasible. In addition, this fill, due to its weight, would probably cause additional settlements. Therefore, the negative effects of the excessive settlements on the island's ability to withstand high tides should be mitigated by extending the height of the sea walls accompanied by their reinforcement. The major source of worry, however, are the differential or unequal settlements affecting the structures, especially the terminal buildings. As I mentioned earlier, in order to compensate and cope with these problems and provide smooth operations, the supporting columns of the terminals are equipped with a jack-up system for periodic adjustments. Regardless of the excessive settlements, the Kansai International Airport remains a monumental masterpiece that has survived multiple typhoons and earthquakes, and it will go down in the history books as a mega project of the 20th century. A lot of insights came from this mega project. For example, the effectiveness of sand columns in accelerating consolidation in marine environments, and the importance of the three-dimensionality when predicting immediate settlements of clays. It also paved way for the development of offshore airport construction on artificial islands. I've been your host, Chido Chasha. Thank you for sticking around to the end of this video. I know this was a little bit longer than my previous videos, so I really appreciate your support. With that, please leave a like and subscribe to the channel. That will mean a lot to me. You've been watching Geotechs with Clemens.